Hello everyone! Astrobot has taken the world by storm this year with its tasteful use of age-old PlayStation IPs. The game features numerous novel particle systems, taking full advantage of the PS5 hardware to dump as many particles on screen as possible. There's also the game Dreams, which is made entirely out of particles, and my personal favorite particle system, the humble fungus spores from The Last of Us 2 that float around in the air and reflect light. All these examples are from newer games. So why is it that novel particle systems are a recent phenomenon? What makes a particle system a particle system? How many particles can my GPU even draw? All of this and more in today's video, where I explain how I accidentally invented a particle system that no one has ever seen before. So what actually is a particle? This question kind of misses the forest for the trees. The definition of a particle is very case by case and depends on the context of all in which it lives in and came before it. What really matters is the particle system as a whole. Take for instance a forest of trees. We could say the forest is the system and the trees are the particles, or a swarm of bugs. The swarm is the system, the bug the particle. It then makes more sense to describe what a particle system is. So I would define a particle system as a collection of entities that all follow the same or a similar set of rules. This means we could call something like Ghost of Tsushima's foliage a particle system, where all of the individual grass blades and flowers are particles because they all behave the same for the most part. Particle systems go beyond physical entities though, and are a driving force of visual effects in video games, such as the iconic Zelda Wind Waker bomb particles or infamous Second Son's novel particle effect system to make the powers as cool as possible. This brings us to the inspiration of today's project. Imagine a point in space centered at the origin. We split this point into 3 new points, where the first point is going to be divided by 2 and move towards the point 0, 0.36. The second point will also be divided by 2 and move towards the point -0.5, -0.5. The third point will also be divided by 2 and move towards the point 0.5, -0.5. And then we repeat the process again with each new point, splitting them into 3 and doing the same operations, and so on forever. Repeating this process an infinite amount of times gives us the very famous Sierpinski triangle fractal. Very surprisingly, from just 3 simple instructions, a world of infinite detail is born, which had me wondering, what happens if we added another position to move to? What if we divided by some number other than 2? To realize this idea, I decided to make use of a particle system to model the shapes created by these instructions. So let's start by learning how GPUs can draw millions of points with ease. But first, something a little different. I'm so excited to announce the channel's first merch apparel. Profess your love for the graphics processing unit with the exclusive Acerola I Heart GPU shirt, available in the US and the EU. I've been struggling to afford spending more time on videos to create cooler and more interesting projects like the one in this video you're about to see. So if you would like to see videos on deeper graphics programming topics like terrain generation, fluid simulation, path tracing, physics simulations, or whatever else, please consider supporting the channel and buying a shirt so I can continue creating free educational resources for graphics. To reiterate the goal, we have a shape that can be created from an infinite number of iterations on a set of positions. In order to render this shape in a game or something, we obviously can't do something an infinite amount of times, so we are instead going to need a very large number of particles to approximate that infinite series, and by extension, the shape. The problem here is that drawing millions of objects can be quite slow, and we want to have at least 60 frames per second. If you remember from all the way back in my video on drawing millions of grass blades, you might think the solution to this problem is GPU instancing, because that's what made the grass possible. So let's start with that approach. When we want to render an object in a graphics engine, the CPU dispatches a draw call to the GPU. This draw call contains the information the GPU needs, such as the mesh to be drawn and where. This draw call is then added to the schedule of actions the GPU must take before the next frame is rendered. This is totally fine in most cases, and how it works for the majority of objects in a scene. Each one has its own draw call. A major problem arises with stuff like foliage though, where there are lots of entities. In the case of my original grass field, we would be looking at something like 20 million draw calls, and thus 20 million scheduled actions for the GPU to take before the next frame is rendered. The GPU will draw this blade of grass, and then this blade of grass, and then this blade of grass, and so on and so forth, forth until the whole field has been drawn. The sheer number of scheduled actions will tank the performance of our game to 0 FPS, and we no longer have a game to play. If we pause and think a moment, we would realize that the GPU is drawing the exact same mesh, just at different positions, so it would be convenient if there was some way that the GPU could interpret our 20 million draw calls as only one and draw all of the grass in one fell swoop. To do this, we supply the GPU with the mesh to be drawn, the number of times it should draw it, 20 million in this example, and then an array of 20 million positions to draw the meshes at. Now, instead of a draw call, we would call this a batch, because it's one scheduled GPU action that results in many draws, replacing the 20 million calls from earlier. This is known as GPU instancing, and it has a number of limitations. The first is that the mesh must be the same for all instances. This is because to make GPU instancing possible, we actually do the simplest, hackiest thing ever. In the vertex shader of the mesh, we supply an instance ID to the shader and use that to index the buffer of positions, which we offset the vertex with. Technically speaking, we are drawing all of these instances at the origin, but after we grab the corresponding position and offset the vertex, it shifts over to where it's supposed to be. Secondly, the buffer of positions cannot be efficiently updated from the CPU at runtime because of data latency between the hardware. 20 million positions from the CPU would crash our game to 0 FPS, and we would no longer have a game to play. So, thinking about our dilemma of needing millions of particles, GPU instancing sounds like a proper solution. It's certainly going to be faster than millions of individual draw calls, but we need to consider how the limitations of instancing will affect our particle system implementation. First, all the particles must be the same mesh. We could use a cube, a sphere, Leon Kennedy, or a triangle, but when most people think of particle systems, they think of point clouds. A point cloud is a collection of points which occupy exactly one pixel. The mesh is only one vertex, no triangles or anything. So this means we will be instancing a mesh of just one vertex, and the batch will result in a point cloud approximation of our shape after all the instances are drawn. The second limitation, that we can't update the positions of the particles from the CPU, is a bit upsetting though, as ideally we would like to be able to move the particles around at runtime. Thankfully, we can make use of compute shaders to operate on GPU memory directly, enabling us to update the particles as much as we want. This is the main reason why cool particle systems have only been popping up in the past decade or so, because compute shaders and the ability to operate on GPU memory directly is a fairly recent technological advancement, whereas previously, particles had to be controlled CPU side. So how can we most optimally utilize GPU hardware to generate a list of positions from the set of instructions I described earlier? Returning to the real topic at hand, we have a set of 3 functions that we want to repeatedly apply to an ever-growing set of positions. In math terms, this is called an iterated function system, where the next output is dependent on the previous output. In GPU land, the word iterated should raise some alarms, as GPUs are meant to do everything in parallel, not in sequence. Let's ignore this red flag for now though, and continue onwards. The base case of our system is a point at the origin. To progress the system, we duplicate that point 3 times and apply each respective function. Then we duplicate each of those points 3 times and repeat until we're satisfied. I'll be referring to each sequential iteration of the system as a generation. The first generation contains 1 point, the second contains 3, the third contains 9, and if we continued, a 4th generation would need 27 points. For those of you with computer science experience, the alarms should be getting even louder now, because this is exponential growth. The amount of points we need to represent a generation of the system is 3 to the nth power, where n is the generation. If you don't have computer science experience, all you need to know is that exponential algorithmic complexity is about as bad as it gets, demonstrated by this deep red color on the complexity graph, describing it as, quote, horrible. This is because the number of particles we need is quickly going to get extreme. Just 16 generations of the system requires 43 million particles to represent it. Even worse, we need to visualize all generations to get a filled out shape, so our memory cost is going to be the sum of 3 to the n. 16 generations would require a buffer of 65 million positions. As far as we know, we just have to bear the burden of this cost, so let's continue onwards. The good news is that we can easily pack this into a single buffer for our GPU instancing. Now for our compute shader, given a desired number of generations, we calculate the sum of 3 to the n and instantiate a buffer in GPU memory of that size. Since generations are dependent on the previous generation, we must calculate each one sequentially. Our first dispatch will fill in the first slot of the buffer with the base case of 0, 0. The next dispatch will be 3 threads that operate on the base case. The next dispatch will be 9 threads that operate on the previous 3 outputs, and so on until we have created all the generations we wanted. As you can see, the thread count also grows exponentially, which is really bad, as there is a limit to the number of threads that can be dispatched at once. An ideal thread group size is 64 threads, and the maximum amount of thread groups that can be dispatched at once is 65,535, or 2 to the 16th. Multiplied by 64 is a limit of 4.2 million threads in one dispatch. That is a lot of threads, but if you recall from earlier, a 16th generation of our system would be 43 million particles, and so we would need 10 dispatches to generate all of those positions, not including all of the dispatches needed to create the prior generations. In the pursuit of a program that runs at more than 0 frames per second, let's keep it so that the number of generated particles can be contained in just one dispatch. With this limitation, we can only create 13 generations of this iterated function system, but that should be good enough. With a buffer of positions created and a single vertex mesh to instance, we draw 2.4 million particles to obtain an approximation of the Sierpinski triangle fractal from earlier as a point cloud. That was a lot of effort to obtain a fancy triangle, and even worse, our algorithm for creating it is about as bad as it could possibly get. If we showed up to GPU land with this, we would be laughed out of the venue and nobody would ever listen to us ever again. Our only choice would be to turn to a life of alcoholism to cope with our failure before dying tragically in a car crash. Hopefully, there's a better way. Wait a second, what even is this shape called? Obviously, it is the famous Sierpinski triangle, something that shows up in many math contexts. But in this case, its technical math term is the attractor of the iterated function system. What we've done to generate this particular attractor is the formal mathematical method that reliably and uniformly creates the shape. You can see that all the points are very cleanly distributed across space at each iteration. As I've demonstrated, this formal method is very inefficient computationally, requires an absurd amount of memory, and actively fights against what GPUs are good at. The Sierpinski triangle is also one of the simplest attractors, requiring only 3 functions, but many more interesting attractors exist of differing function set sizes. The cost of a formal iterated function system is thus k to the n, where k is the function count and n is the generation. Thankfully, this formal method is not the only method, and a better one can exist for our use case. Imagine a future version of our iterated function system that has freely surpassed its computational and memory limitations. Domain expansion. The chaos game. It's incomplete. It's ugly work at best, but for now, that's fine. The chaos game is a stochastic method for generating the attractors of iterated function systems. It works in almost the dumbest way possible. All we do is randomly apply the functions from the set to the positions of the particles, and the points will converge all the same. There is no need to calculate multiple generations sequentially. The entire buffer can now be updated in one single compute dispatch. There is no longer a restriction on particle count based on generation size. The chaos game works on any number of particles. The more particles there are, the better the approximation of the attractor is. The chaos game is an absolute win. It reduces the complexity from exponential to linear, lifts the restriction on particle count so we can choose any amount of particles we want, and takes full advantage of GPU hardware by updating all the particles at once in parallel instead of in sequence. Of course, the shape is now noisy, but there are many ways to fix such an issue. Now that we can efficiently generate attractors, it's time we started generating more interesting shapes instead of just the Sierpinski triangle. Wait a second. Why does this set of functions even result in a cool shape? Looking a bit closer at one of these, x is a 2-component vector, so let's expand each component. X and y are divided by 2, which is another way of saying multiplied by 0.5. These added values here are called translations, which simply moves the position of the point through space. For fun, let's add the missing variables to both lines multiplied by 0, and we have revealed a dubiously unrolled matrix multiplication. This is true of every other function function too. We can generalize them to the form ax plus b, where a is a transformation matrix and b is a translation. This combination of a transformation matrix and a translation is called an affine transformation, and it can be represented as a single matrix multiplication by adding an extra row to the matrix with a 1 at the end. This is known as an augmented matrix or affine transformation matrix. Fun fact, when working with three-dimensional coordinates, transformation matrices are 3 by 3, so an affine transformation in 3D would require a 4 by 4 matrix. This is why matrices in Unity are 4 by 4. With this new information, we can rewrite all the functions in our iterated function system as affine transformation matrices, and now when we update our particles, we simply multiply the position with a random matrix from the list. Why would we do this? Because now we are free from the strict definitions of functions, and we can easily slot in different matrices to generate new attractors. But before we can do that, we first need to understand the humble matrix transformation. Transformation matrices represent linear mappings, or in simpler terms, the instructions for moving from one space to another. Consider our usual normal world, where 1 meter is 1 meter. Now consider a different world, where everything is half as small. 1 meter is now 0.5 meters. The map to this alternate world can be described with a scaling matrix. Putting 0.5 along the diagonal will uniformly reduce the scale of a position to our new, smaller world. This is exactly what's happening to our particles. Every iteration, a particle is mapped to a smaller and smaller world. It can never grow larger, and so it always converges to the fractal shape, never escaping. Scaling is not the only kind of linear mapping though. There's also rotation, reflection, shearing, squeezing, projecting, and more. And the amazing thing about matrix multiplication is that you can multiply a whole bunch of them together to create a cooler matrix that does all of that multiplication at once. Keep in mind that matrix multiplication is not commutative, and the order matters. For this video, I will be using scale, rotation, shear, and translation. This is, of course, a ridiculous amount of settings and parameters to mess with for just one affine transformation, and we can have any amount of them in our system technically. So to make our lives easier, let's randomly generate each individual transformation before combining them into a single affine transformation matrix for our iterated function system. Now, every time I press the Generate Shape button, we are met with a new and exciting fractal shape that's a bit different from the Sierpinski triangle. Given the statistical likelihood of these shapes being generated, it's quite unlikely that anyone has ever seen these shapes before, so congratulations on being the first people to see them. Because of the nature of the chaos game, we can easily swap sets of transformations in and out to update our particles without completely resetting the particle system, which is an idea I wanted to explore even further. How could we more cleanly blend between these shapes? On the topic of blending, there are many approaches, and it comes down to artistic preference eventually. Blending values of any kind usually starts with a very simple equation. Given two values that you want to blend, a and b, and a blend factor t, the blended output is 1 minus t times a plus t times b. When the blend factor is 0, b is cancelled out and we only get a, but when the blend factor is 1, a is cancelled out and we get b. When the blend factor is 0.5, we get the average of a and b, or the middle point between them. This equation is known as linear interpolation, or LIRP for short, and is the common foundation for blending anything you want, whether that is scalar values, vectors, angles, positions, colors, or even matrices. On the topic of blending iterated function systems, the naive approach would be blending the positions directly by calculating both attractors and then blending between them. Unfortunately, this requires double the memory, 2 buffers for each attractor, and double the memory fetching when we inevitably blend the two. You might think this at least results in a decent blend, but it doesn't. Blending the positions of 2 attractors doesn't look that good. It's stiff, direct, and doesn't truly illustrate what a blended attractor should look like traveling through space. There should be like rotations and shit. So for double the memory cost, we also get a worse result. Thankfully, because of the chaos game, we can decouple the blending from the positions and instead blend the transformation sets for a better result while still operating on only 1 buffer in memory. We have another problem though. Directly blending affine transformation matrices gives very poor results. Blended matrices look like they do transformations they aren't supposed to, such as this one that is shearing space even though no shearing transform is involved with the original matrices. So we unfortunately have to take the blend another level higher and blend the individual transformations before they are combined into one. Blending at this level gives much better results. The shear from the naive blend is no longer present. present. Now when we interpolate attractors, the movement of the particles is far less direct, rotating through space like they should, instead of traveling along a straight line. We have yet another problem though, which is that linear interpolation is very ugly. It's stiff with no soul. The traditional solution to this is easing functions that operate on the linear blend factor, making it non-linear so that the blend has more character. An amazing website exists with a collection of different easing functions called easings.net, but since I'm using Unity, we can just use an animation curve. This is really an easy way to instantly make your animations more interesting and less robotic. I was still less than satisfied with these easing functions though, so I decided to implement Freya Holmer's frame rate independent lerp smoothing, which is the only animation method I tried that gave the impression the fractals were truly growing out of each other, and the results are stellar. Conceptually speaking, the lerp smoothing exponentially decays our attractors towards each other, and you can read more about it in Freya's blog post on the topic, in which she also goes into more details on frame rate independence and linear interpolation. The rules of our particle system are now complete. We can procedurally generate and blend between three-dimensional iterated function systems all we want for infinite, never-before-seen entertainment. This is only 1 million particles though, which, to be honest, is rookie numbers, so let's see just how many particles my GPU can handle. It's time for a performance pop quiz. Get the answers right, and you just might win a prize. As a quick recap, our particle system works by updating a buffer of positions with compute shaders that randomly multiply the positions with matrices. This buffer is then supplied to an instancing call in which we draw as many single vertex meshes as we need. These particles are displaced in the vertex shader by fetching their corresponding position in the compute buffer, resulting in a point cloud approximation of the attractor after everything is drawn. With this implementation in mind, how many particles do you think my mid-tier GPU can handle before it dips below 60 frames per second? Is it 10 million particles, 40 million particles, 100 million particles, or 200 million particles? If you answered 10 million, then you're correct. Wait a second. We can only handle 10 million particles? It said 100 million in the thumbnail or the title of the video. Okay. Well, time for a different question. Clearly there's a bottleneck somewhere that is heavily limiting our particle performance. So let's take a moment to ponder what those bottlenecks might be. The first stage of our particle system is the compute shader dispatch. Is it possible that updating 10 million positions in one frame is just too slow? The second stage is the vertex shader. 10 million particles is quite a lot of memory, nearly 120 megabytes in fact. Is it possible that fetching the position from global memory in the vertex shader is too expensive? The third and final stage is the fragment shader, when the particle is drawn to the screen. There's several potential issues here. The first is something called subpixel triangles. The rendering pipeline has some implicit overhead costs. When we render to a pixel, we actually evaluate it in a 2x2 grid of pixels to calculate data for some other rendering pipeline features like mip-mapping and derivatives. This is almost always desirable because generally objects we render occupy more than a single pixel. Unfortunately, because we are rendering points, every single one we render is only occupying a single pixel, yet we still must pay for the overhead of the rendering pipeline anyways, and evaluate the 3 neighboring pixels, even though there's nothing there. Each one of our points actually costs 4 points. Are the 10 million subpixel points harshing our vibe a little too much? Another potential issue is something called overdraw, when we draw to a pixel multiple times, wasting the work that was previously done. Since we're drawing millions of particles on top of each other, this could also be bottlenecking our program as we write to pixels many more times than we would want to. So, is the dastardly fragment shader the source of our poor performance? I ran a Twitter poll to see what you all thought, and the common sentiment was that the fragment shader is the culprit. The subpixel triangles and overdraw is just too much for our poor 1660 to handle. Unfortunately, you're all wrong. It's the humble vertex shader that is to blame for our poor performance. The memory fetch is just way too expensive. Our GPU actually couldn't care less about the 10 million subpixel triangles. Keep this in mind next time an armchair developer on Twitter says some bad topology is the reason the game runs so poorly. All 10 million positions are updated in about 1 millisecond as well, so the compute compute is inconsequential. Thankfully, there's a way to completely subvert the memory fetch in the vertex shader and unveil the path towards drawing 100 million particles. Admittedly, we've gotten lost in the sauce. GPU instancing a single vertex mesh is quite the big stink, and we are using GPU instancing in place of the simplest method, just using a mesh to hold our data. Compute shaders can operate on the vertices of meshes directly, so if we had a point cloud mesh, we could modify its vertex data each frame and then tell the GPU to draw it, streaming in the newly updated positions rather than fetching them in the vertex shader. We're still using the same amount of memory, but now the positions are grabbed automatically and streamed in to take full advantage of what the GPU is built to do, chug through millions of vertices. We can create meshes with vertex counts that fit within a single compute dispatch and update their vertices in no time at all. But remember that because our point cloud meshes are now unique, we can no longer GPU instance, as that required each mesh to be the same. With this restructuring, we have eliminated the costly memory fetch in the vertex shader, and our 1660 can now draw 100 million particles in just 115 milliseconds. That's about 9 frames per second, so not very good. Unfortunately, 100 million is just a little much for our 1660 with this method, but we did increase the maximum from 10 million to 30 million, which is a substantial increase. Still, I can't stop thinking about the 100 million goal. I sat and stared at my wall for hours, racking my brain for any new ideas, any possible solutions, but nothing came to mind. So I stood up and went into my kitchen to find a solution. An NVIDIA RTX 4090. Slotting it into my computer, the 4090 can handle 100 million particles just fine. We finally did it. 100 million particles. But I'm still disappointed with this particle system so far. To be quite frank, it looks like shit. Our iterated function systems are 3-dimensional, but because of the flat shading, it looks 2D from every angle, completely defeating the point of the 3D particle system. What if I told you that a world of infinite detail was hiding underneath that flat coloring? In order to see it, we're going to need to implement a lighting solution, anything that can give the 3D volume some sense of form. But how could we possibly light 100 million particles in real time? We need some kind of shading to see the true detail of our iterated function system, but all we have is millions of unsorted particle positions to work with. If this was the future, maybe we could just ray trace the particles, but even a simple naive shadow trace would require 100 million squared comparisons, and that's a little much for even our 4090. What I'm looking for is the absolute bare minimum, so I'm going to do this in the most brute force, dumbest way possible, and I need to clarify that this is a proof of concept. It is hardly optimal and only made possible by the 4090. Do not try this at home. If we ensure our iterated function system stays within a certain bounds, we can divide up the area into a set number of voxels. Then, each frame, we are going to iterate through our particles and turn on the nearest voxel to its position, which will give us a rough approximation of the volume of our point cloud. With a voxelized version of our particle system, we are free to do any sort of volumetric lighting techniques we want. We could ray march it like we did back in my Counter-Strike 2 smoke video to get a cool smoke-like effect if we wanted, but unfortunately, we need millions of voxels for accurate shading here. Even the 4090 probably can't handle ray marching this. Instead, we're going with the simplest lighting possible, an ambient occlusion approximation. We iterate through every voxel to determine how many neighbors it has that are filled in. The more filled in neighbors, the higher the occlusion value. Then, in our particle fragment shader, we are going to sample the voxel grid based on the position of the particle to determine its shading. Now, we can finally get to see our beautifully shaded, 3-dimensional iterated function system approximated by 100 million particles rendered in real time. It's not the best solution in the world, but it's certainly one of the first real-time lighting solutions for iterated function systems ever invented, because this is pretty much only possible on the 4090. Once again, you're seeing something no one has ever seen before. Did you think we were done? No. This makes me sick. Only 100 million particles? What is this, amateur hour? Let me show you how we can double the particle count for basically free, taking advantage of every idea in this video so far. I hope you haven't forgotten about the formal method for generating attractors. Remember how the base case of the formal method was a single point at the origin that we split into however many more we need for the next generation? What if we instead used one of our chaos game approximations as the base case, and we use GPU instancing to duplicate the mesh into the amount of particles we need for the next generation? Consider a 1 million particle chaos game mesh and an iterated function system of 3 transformations. We GPU instance the mesh 3 times, and based on the instance ID, we progress the mesh 1 iteration forward in the vertex shader, just like we would in the formal generation method. This gives us an extra generation of 3 million particles with only 1 million in memory, and all it costs is an extra matrix multiplication in the vertex shader. I'm sorry, formal mathematical method for generating IFS attractors. Perhaps I treated you too harshly, because now we can render not just 100 million particles, but 205 million. Our particle system is complete, making use of both methods of attractor generation by applying the chaos game technique to simple point cloud meshes, which we then instance copies of with the GPU to get an extra generation for free by applying the formal technique, then using a crude voxel approximation of the point cloud to provide basic ambient occlusion as a form of lighting. As far as I'm aware, I am the first person to create a 3-dimensional iterated function system point cloud with a real-time lighting solution that is optimized to this degree. The only real literature I could find on iterated function systems and graphics was this article from 1990. Now it's time for everybody's favorite part of the video, making it look good. It's hard to describe what our particle system really looks like. The material is very strange. It reminds me of moon sand. It looks soft, yet granular. We can change the color of the particles and the shadow color all we like. A lighter shadow color makes the particles look fluffier and more volumetric, almost like a cloud. Because of the chaos game, our shape is stochastic, which is a really pretentious way of saying it's noisy. We could fix this with something like temporal anti-aliasing or some other analytical denoiser, but I don't have an implementation of TAA or a denoiser on hand, so I went with the Kuwahara filter. The Kuwahara filter is an advanced post-processing technique for making images look stylized and painterly, and it has a huge effect on our particles just by itself. Lastly, some bloom really pulls it together, but I need to make a better bloom shader soon, as my Unity one isn't the best around. Please enjoy 30 seconds of epic particle system shape-shifting action. Here's a few screenshots I took during development as well. This one is my favorite thing I've ever rendered, I think. And this is where my journey into iterated function systems ended for now, but there's still a million ideas left to explore. So let me dump some ideas onto you all, just in case you want to pick up where I left off. It can be really hard sometimes to conceptualize applications of stuff I make videos on, so here's a bunch of potential use cases and extensions for this tech. In this video, we only subverted the cost of the vertex shader memory fetch. It is actually possible to subvert the entire rendering pipeline with a custom compute replacement known as splatting. In fact, Gaussian splatting is all the rage right now. With splatting, we could potentially render not just 200 million particles, but over a billion easily. The problem is that splatting is not really compatible with game development, and the methods I presented in this video are. If you would like to see a video where I render billions of particles with splatting, please buy a shirt, thank you. Iterated function systems could be used for voxel propagation for volumetric effects such as clouds. When I was flying home from Seattle the other month, I was staring down at the clouds and I saw something very similar to a fractal IFS shape. The formal and chaos game methods aren't the only methods for generating attractors. In fact, you can play with the generation rules as much as you want to create even more interesting shapes, such as restricting certain particles from iterating in something called the restricted chaos game. Right now, each one of our transformations has an equal chance of being applied, but there's no need for that to be the case. We could assign probabilities to each transform to accentuate them. For instance, maybe one has a 50% chance to be applied, and the other two have a 25% chance. This results in even more interesting attractors as shown here. Many real-life objects objects are fractal in nature, such as coral, mushrooms, ferns, trees, and other foliage. You could certainly use iterated function systems to procedurally generate meshes of these objects. Many algorithms for converting point clouds to meshes exist. This has already been done with stuff like L systems, which are a form of iterated function system that operate on strings, so it should be easily adaptable to this context. Can we draw with fractals? This specific iterated function system results in a quad. We can expand it into a cube as well. Could we stack a bunch of transformed sets of this cube IFS and draw objects purely with iterated function systems, just like we can with signed distance functions? Right now, the colors of our particle system are manually controlled. One way to improve the procedural generation would be hooking up my procedurally generated color palette techniques from my video on the subject to also procedurally generate colors for the system to blend between without looking terrible. In fact, since color spaces are a space like any other, perhaps iterated function systems could be used to generate color palettes as the positions travel through the color space. Lastly, the noisy nature of our fractal is a legitimate concern. The Kuwahara filter is a poor denoiser, so it would be interesting to see how much temporal anti-aliasing could mitigate the noise. Well, I hope you enjoyed this deep dive into linear algebra and advanced graphics programming techniques. I wanted my first video with the 4090 to really push the limits of what's possible, but don't worry, I'm still mainly developing on the 1660. Again, if you'd like to see more videos like this one where I can do actual research and development and push graphics programming tech forward, please consider buying a shirt or supporting the channel on Patreon. As usual, a huge thank you to all my current patrons. Without your support, I wouldn't be able to stare at my particles for so long that I see fractals when I close my eyes now. Anyways, that's all from me. I hope you have a great rest of your day, and I'll see you next time.